Great, so my presentation is going to be on the normal distribution and what exactly is so normal about it. The basics to start off is I'm going to describe what a distribution is, kind of give you the background on that so we know how to put it in context, and then I'm going to, that shouldn't be on there anymore, I'm going to go over some examples and applications so you can see exactly where it appears and how it comes up. But first, to explain to you what a distribution is, we're going to think of a single die. When you roll this die, as I'm sure many of you are familiar with, you can roll the numbers 1 through 6, such as that. And each face that will land face up has an equal chance to be rolled. Roll it, you get a 2, roll it again, you get a 5, roll it again, you might get another 5, because that's how randomness works. But if you roll it millions and millions and millions of times, at the end of the day, or week, if you're rolling it that many times, your distribution will look like this. Each number will have appeared about the same number of times, and this is a type of distribution called the uniform distribution. One of the key things about a distribution is that all of the events that occur have to, their probabilities have to add up to be 1 or 100%. This is where we left off, where I didn't have my slide. And as you can see now, all the numbers 1/6, 6 times, all adds up to be 1, 100%. Like I mentioned, this makes the uniform distribution. But then if you roll 2 dice, like I was mentioning before, your distribution will look something like that. As you can see, 2 only has 1 way to occur, 12 has 1 way to occur, and 7 has 6 ways to occur. What? Oh my god, I'm so sorry. That is because each of these combinations of either a 1 and then a 1, a 2 then a 1, 3 then a 1, 4 then a 1, all creates a different occurrence that can add up to 7. There are 36 total ways, and if you were to add all of these up, you would get a total of 36 over 36, which is 1. So it is a legitimate distribution. But then we need to look at the normal distribution. About time I talked about it. This goes from negative infinity to infinity all across the real line. And so because of that, we can't exactly look at this the same way we looked at the other ones. Because if I just took 1 point, obviously that 1 point over, the chance of giving that 1 point over an infinite amount of points is 0, because 1 over infinity is 0. But what we remember from calculus is that we can look at the space underneath the curve as a series of teeny tiny itty bitty little bars. You know, it's like Wisconsin. Teeny tiny itty bitty bars. So we can look at it that way and add them up, and that's Euler's method. Or we can use integrals and add up the entire area underneath the curve. To do that, of course, we need the function for the curve, which we know to be 1 over sigma times the square root of 2 pi times e to the negative x minus mu squared all over 2 sigma squared, which is a mess, and no one wants to look at that. But luckily, it is pretty easy to integrate. If we integrate it, we obviously just set it up, take out our constant, and then we have this integral right here, which is a known integral, the Gaussian integral. Looking at the way that Gaussian integrals work, we know that this integrates down to sigma times root 2 pi, multiply that times our constant, which is 1 over sigma root 2 pi, and of course that equals 1. So this is a legitimate distribution, thank goodness. But how is it normal? How is this arbitrary looking shape, this little bell curve, with this really wonky formula so normal? To explain that, we'll have to look at some applications. The first is a pretty easy one to see. It is the distribution of heights between men and women. As you can see, these both create a bell-shaped curve, a very normal looking curve. This happens in biology a lot. Another place we can see it is some scientists measured the packet delay variation. A packet is a little bit of information that you send through the internet. They measured that delay and the variation there, and this also turned out to be normal. And again, a biologist measured the HDLC. It's a chemical in some insects known to be in a population that carried a disease, and this turned out to be normal. This distribution happens everywhere. I mean, this pile of sand with a dog on it. You laugh, I heard you laugh. It's normal. It happens everywhere. It naturally occurs in many, many places. Even means, means especially, are normally distributed. In fact, every mean is normally distributed, as we can see by this little apple here. Zoom in a little bit so you can see better. It's not showing on here. Well, I won't zoom in. There you go. So we have this distribution, some kind of distribution. What we're going to do is we're going to take 5 random samples from it, like so, and then take their mean and drop it right there where their blue is. Take 5 more, take the mean, and drop it right there. Speed this up, I'm just going to go ahead and take 10,000 samples. Lo and behold, it's approximately normal. This happens with other distributions too, any distribution. Can someone give me, how should I shape this distribution? Just wonky or how?
2 high points, 2 modes.
2 high points, like that, like that. Sure. So then we again do 10,000 samples. It's kind of ugly, but it's approximately normal. You can do a dip, 10,000 samples, and still approximately normal. Every mean that you take is approximately normal, which is just fantastic, because that means that any scientific study, whenever you're taking some kind of random sample and taking the mean, you always know exactly how it's going to behave. And that is like mind-blowingly amazing. It makes everything so much easier.
2 minutes, yeah.
2 minutes, thank you. So the distribution appears everywhere. It appears in the easiest of science experiments, and it appears in biology. And it even appears here, well, okay, I guess this isn't really normally distributed as it kind of goes wonky, wonky, wonky. Or wait, if we look, this red line here is the average sea level in North Carolina. These are the error bands, positive and negative, which means that it's just hiding. The normal distribution is right there across the error. It's literally everywhere, and that's what makes it so normal. This little distribution shows up in so many places, across so many fields, and at the end of the day, it's basically magic.
Very good.